Good afternoon, everyone. I don't think I do need to introduce myself after having 2 meetings with the HAO staff. You all already know that my name is Vanda Grubisic and I am the chair of the selection committee for the HAO director position. So I'm making this announcement for everyone else who is following us over the webcast. The presentations in the following 3 days will be webcast. So I certainly hope that a number of people are following us behind, sitting at their desks and following the presentations and everything that will be happening here in the next 3 days. The presentations will also be recorded. And as a housekeeping remark, I have asked all the candidates to repeat the questions if necessary so that it is clearly recorded before they start answering the question. As you all know, we have 3 candidates, 3 finalists for the position of the HAO director. All 3 of them are familiar to you. All 3 of them are the HAO internal candidates. I do want to make a short remark about that. The selection committee, who is sitting in the back, except for me and Betty Otto-Blisner, who is out of town, but nevertheless she is taking part in all the proceedings. We have carefully examined the pool of applicants, and striving for the best qualified candidates, we have come up with a finalist list that consists of the 3 internal candidates. That does not mean that there were no external applicants for this position, but as in any process, you cannot say what the outcome will be when you start, and we strived for the qualifications, and here are the finalists that we present to you. Now I want to turn the attention to Stan Solomon, who is the first to interview, who is opening the 3-day sequence. I might have to look up in the materials to say a few things about Stan. You probably know this better, some of these things better than I do. And so, but it is formal process here. So I will start by saying, recapping shortly his education. 1987, PhD from the University of Michigan, Ann Arbor. 1982, Master of Sciences, also from the University of Michigan, Ann Arbor. And going back, 1975, AB, and this is an interesting AB in psychology and social relations at the Harvard College, Cambridge, Massachusetts. Certainly something that would help potentially in this job. So, reviewing shortly his career, he started as, if I recall correctly, he started as a postdoctoral. Actually, he started as a research fellow at the Space Physics Research Laboratory at the University of Michigan, and then became the postdoctoral scientist in the High Altitude Observatory. In 1987, he stayed with HAO for 2 years, and then moved on to not very far, to the University of Colorado, to the Laboratory for Atmospheric and Space Physics, where he had stayed for about the next decade, both as a research associate and also in lecturer, a research associate in LASP and the lecturer in the Astrophysics and Planetary Science department. Since 2002, Stan has been with HAO. He has been with NCAR, starting as a project scientist 3, and then becoming scientist 3, changing the track, coming over to the latter track. In 2005, he became the deputy director of HAO and was in that position for 4 years. In 1 year as an acting director, 2009-2010. And present since 2006 to the present, he's a senior scientist in the AIM section of HAO. He's widely published. He has more than 145 papers to his name. And at this point, and a long record, I should also say, of professional service with NASA and the other number of other organizations and high-level boards and panels. At this point, I will turn the stage to Stan. But before I do that, you see the title of his presentation. I should also say that we have given the guidance, the selection committee has given the guidance to the candidates, and the presentation is not going to be, at least that's what we expect, not to be just a science talk as the title would suggest, but also addressing the management issues related to the position for which the candidates are interviewing. The presentation is scheduled to be about 45 minutes, and I carved out 5 minutes already out of that, and followed by the general question and answer period. So, Stan, without further ado.
Thank you. Maybe we should turn this one off. It's off. You did. Thank you. So let's keep it informal. Please interrupt with questions if you have them. And if you can't see this screen, I can kill this front light for some of the darker stuff. So just call out if you want me to make an adjustment. I am, in fact, going to give 2 talks. First one on some of the things we've been working on recently pertaining to the variability of the sun and the effects on the upper atmosphere, solar and geomagnetic, anthropogenic, atmospheric drag, and the recent solar minimum, or the solar minimum of several years ago now. And then I'll give another brief talk just discussing what I think is our frontiers in solar terrestrial physics and how HAO can play a role in that. So the solar cycle is best described in sunspots simply because the record goes far back in time. And here I've plotted the monthly mean sunspot number in black dots and the annual mean in a red line. The amplitude, and of course immediately you can see the 10 to 12 year periodicity of the solar sunspot cycle, which is indicative of changes in general activity on the sun. Prior to the period of time when this plot starts, there was an extended period over 50 years. There were very few or no sunspots, possibly indicating very low activity. And if you look at this, you can see there's significant change in the amplitude of the cycle. Whether that is a random variation or there's some regular pattern behind it or some chaotic quasi-random change to it, I don't know. But you could well imagine that seeing as how there have been periods even since this Maunder minimum period of very low activity, when sunspot activity was low, such as the Dalton minimum, and then again about 100 years ago, you might imagine that the space age, which was characterized by very high solar activity, perhaps is drawing to a period when things are starting to change again, or not. Maybe it's just random. So the sunspot activity correlates very nicely with extreme ultraviolet radiation and all ultraviolet radiation, and also X-rays. In this case, I'm going to focus on extreme ultraviolet radiation because it's so important to the upper atmosphere of the Earth, especially the thermosphere and ionosphere. This is a plot from the set of images from the EIT instrument on the SOHO spacecraft, going from solar minimum in '96 up through solar maximum, then back down to solar minimum, or almost solar minimum, in 2006. And you can see how there is extreme ultraviolet radiation at this particular wavelength, 30.4 nanometers from helium. It's throughout the solar disk, but then it gets concentrated in these active regions. These are so-called plage or beach regions where particular intensity of the ultraviolet radiation occurs, and that's very well correlated with solar activity, and it changes with the solar rotation as well. And this then is what the solar spectrum looks like in a simple model portrayal. What I've done is I've taken a model solar maximum spectrum in red and then plotted a solar minimum spectrum in front of it in yellow. So the red fringe is essentially this variability from maximum to minimum, or from minimum to maximum. And starting from the short end, you can see that in the X-rays you have order of magnitude variability, factor of 2, factor of 3 in the extreme ultraviolet, Lyman alpha, maybe 50% or more. And then in the far ultraviolet, 100 to 200 nanometers, the variability is small, 10% or so, but still visible. In the middle ultraviolet, there is variability, just a few percent, but you can't even see it on this plot, which extends. It's a logarithmic plot. It's several orders of magnitude. So as you get closer to the visible, the variability becomes smaller and smaller until at the visible it's less than 0.1%. And in fact, integrated over the whole spectrum, the total solar irradiance is thought to vary over the solar cycle by less than 0.1%. Nevertheless, a lot of that variability occurs at the wavelengths that are consequent to the upper atmosphere, especially the thermosphere and ionosphere. The reason for that, and this time I'm going to start at the long end and work shortward, is that the visible radiation can penetrate to the ground. Ultraviolet radiation gets absorbed in the stratosphere, largely by ozone, which is a fortunate thing for us, and then by molecular oxygen as we get down into the far ultraviolet. This is the region that creates ozone through the destruction of molecular oxygen. And then that dissociation of molecular oxygen happens all the way up into the thermosphere throughout the far ultraviolet until we finally get to the extreme ultraviolet, where we have all that variability, factor of 2, factor of 3, and it's absorbed above 100 kilometers, and this shortward of 100 nanometers is ionizing radiation. Therefore, it creates an ionosphere, which is embedded within that thermosphere, which is the hot region above 100 kilometers. I'm just going to continue with this tutorial for a minute to give you a grounding in thermosphere ionosphere system if you don't have it. Because that solar EUV is so variable, we have a great change in temperature from solar minimum to solar maximum that occurs above 100 kilometers in the thermosphere. Now, the thermosphere is hot because it has trouble getting rid of heat. It doesn't have the molecules that are active to radiate it away. It conducts fairly poorly. So the heat builds up at high altitude, and of course there's an increase in the energy input as the EUV increases. Therefore, solar maximum is hotter than solar minimum. And it's also more dense. The reason for that is as the temperature increases, the atmosphere density increases as the atmosphere swells up. The other thing that's interesting to note about the thermosphere is that above this sort of fuzzy boundary at about 100 kilometers, the atmosphere becomes diffusively separating. And what I mean by that is, instead of being fully mixed by turbulent processes, as it is throughout the atmosphere up to about 100 kilometers, where the mixing ratios of the major constituents are approximately constant, once you get to a region where the gravity waves break, turbulence breaks down, and diffusion, molecular diffusion, becomes an important process, the lighter stuff floats to the top, and the things that are lighter, like atomic oxygen, take over and become the dominant density in the upper thermosphere. The other reason that atomic oxygen is dominant in the upper thermosphere, of course, is that molecular oxygen is being broken down by dissociation, turning into atomic oxygen. So in the thermosphere, molecular nitrogen and atomic oxygen are the main species, with atomic oxygen taking over at high altitude. Embedded in the thermosphere is the ionosphere. You don't normally see them on the same plot because their densities are so different, but the ions are a very small component of the thermosphere. We often just speak of this region as the ionosphere because it was discovered first, and because it's better known, and because it's very consequential for communications, navigation, things of societal importance. But even at the peak of the ionosphere, here in the so-called F region, the ionization is only about a part in 1,000 of the neutrals. So it's a very weakly ionized plasma. As you get down into the E region, this is the lower ionosphere near 100 kilometers. It's more like a part in 1,000,000 ionized. So the thermosphere is largely a driven system. The ionosphere is driven by both the thermosphere and all of those external forces, and the sun, the heliosphere, the magnetosphere, and the rest of the atmosphere all contribute. And the mechanisms for doing so are both direct and indirect. Here are those ultraviolet and X-rays that are absorbed high in the atmosphere and create the ionosphere that I spoke of. There's another mechanism by which the sun can impact the thermosphere, or set of mechanisms, which is the solar wind and interplanetary magnetic field, IMF, which is transmitted through the heliosphere, impacts the magnetosphere, and creates auroral currents and heating of the high latitude ionosphere. Another mechanism, which I won't really have time to talk about, is energetic particles, which are generated in the corona and in the solar wind, and also enter the high latitudes of the Earth's atmosphere. At the same time, The thermosphere is part of the atmosphere, and there is an increasing appreciation for the importance of lower and middle atmospheric forcing through the mechanisms of tides, planetary waves from the middle and lower atmosphere, and then turbulence and convection, which tends to break in unpredictable ways near 100 kilometers and provides the dynamical background that changes the thermosphere-ionosphere system. So one of the tools we have for trying to understand this very complex region is the NCAR series of thermosphere general circulation models. These are models originally developed by Ray Roble, Bob Dickinson, Art Richmond, and many colleagues here at HAO. And also this particular edition, the TIE GCM, where E is electrodynamics, is the atmosphere-ionosphere element of what we call the coupled magnetosphere-ionosphere-thermosphere, or CMET model, which couples to an MHD model of the magnetosphere. It's an open source community release. It's publicly available. It's supported through activities here at HAO, primarily led by Ben Foster, and it can be run with high latitude inputs either from the MHD or from empirical models, including one that's driven off of the interplanetary magnetic field and solar wind, the Weimer potential model. So this is just a cartoon of the ionosphere. Actually, it's a model output, a plot of a model output in the ionosphere, but I have some somewhat more compelling output that might interest you. These are plots of the E region, lower ionosphere, the temperature in the upper ionosphere, well, middle ionosphere, I should say. In red here, the atomic oxygen to molecular nitrogen ratio. This is a dynamical tracer because it responds to vertical motions in the thermosphere, and therefore also is a very important observational diagnostic. So I make a plot of this O to N2 ratio that we like to look at that's representative of the fundamental composition of the thermosphere. And then all of these things impact the high altitude electron density in the ionosphere. This at the peak of a fairly famous storm, the so-called AGU storm, now some years ago. So I can set this into motion and try to explain how this occurs. First, here's the E region with the rotation of the Earth, and there comes a big auroral outbreak, here represented by an increase in electron density at high latitude. What that does is it heats the thermosphere first at high latitude and then throughout the globe as these temperature waves spread through the entire thermosphere. It's not just a polar phenomenon, these big storms. They impact the entire thing, and then you can really see that in the O to N2 ratio, where the dynamics change all the way down to low latitude. All of these things, electric fields, composition, chemistry, and neutral dynamics, affect the F region ion density, electron density, and cause a great deal of variability in the ionosphere, negative storms, positive storms, and all of the unpredictable ionosphere behavior that we try to understand. I'll let them run together. It's a little confusing if you try to track them all at once, but you can see the storm outbreak, the neutral temperature, the big wave of composition change, and the change in the F region. I'll just let it loop for a minute so you can appreciate the dynamism of the system. Here is the here one more time with the auroral storm. Here's the auroral outbreak, and then temperature waves, changes in composition, electron density. Now, one of the reasons, or one of the rationales for these studies is the importance of the atmospheric drag problem. This is the drag on objects in low Earth orbit, meaning the altitude the space station flies, say 400 kilometers and environ. And if it weren't for atmospheric drag, we would have a very easy time predicting the orbits of satellites and other bodies in space, because it's essentially a two-body problem. You can use Kepler's laws to very accurately predict where objects will go. However, because the atmosphere is variable, the drag is variable, this perturbs the orbits, makes things difficult to track. And even though we've made all these advances in understanding, the operational community is still using basic empirical models from the 1970s. And these aren't even the empirical models that you might use in your research, like MSIS. They are primitive models based on early satellite drag measurements that are also run by these very, very coarse solar and geomagnetic indices that are known to have deficiencies. So we think it's time to move this type of activity towards numerical models, full physics numerical models that are capable of of following the same track that meteorology has taken over the past century or so, of moving from empirical descriptions to realistic physical numerical modeling. One of the ways that we can investigate, calibrate, validate, and improve these models is the satellite tracking data itself, since that is not only a good measure of the thermospheric density, but also is in fact the thing that you would like to be able to predict. So we've been using the satellite drag data as a metric for the model development. This is a very coarse way of looking at it, but a very long one. These is an 18-year run that Liang Chen and I did a few months ago that it just investigates the global mean density at 400 kilometers. 400 kilometers is a good benchmark altitude for satellite drag. It also happens to be the approximate altitude of the space station. And so what's shown here is in red, the model. Every dot is a daily mean, global mean. And in black is a satellite drag measurement. Every dot, a daily mean, global mean. Now, the solid lines that are underneath all those dots are the 81-day average. And so you can see several things in this plot. Of course, most obviously, the order of magnitude variability in thermospheric density that occurs across the solar cycle as you go from solar min to solar max, back down to solar min, and now to this rather wimpy solar maximum that we're in now. And several other very salient points. If you look closely, you can see the 27-day rotation of the sun, modulating both the geomagnetic and the EUV irradiance. And then you can see the big storms. Here's some of the famous ones. These big spikes are all geomagnetic storms that perturb the system and increase the temperature and increase the density. You can also see this important seasonal variation. There's a annual and a semi-annual component to it. And it's most obvious here at solar minimum when everything else quiets down. You see the sort of characteristic M shape in the 81-day smooth. And that's an active research topic. It's clearly related to atmospheric processes, but the exact mechanisms are still somewhat opaque. So we think that we're really making progress on our ability to describe thermospheric densities at this crucial altitude. But as we improve the resolution of the modeling tools, we hope that satellite drag studies will facilitate the transition to operations, and we in fact are working with a group on implementing some of those in a test bed sort of scenario. Now, on top of this, all of this variability, there is a relatively new component that was in fact predicted in 1989. A seminal paper by Ray Roble and Bob Dickinson said that even as the carbon dioxide builds up and the lower atmosphere warms, the upper atmosphere will cool, and this will be particularly noticeable in the thermosphere, where we expect, just look at the solid lines here, for a doubling of carbon dioxide, we expect an increase over the course of about 100 years. We expect a decrease in thermosphere temperature by about 50 K over the course of about 100 years, and that will cause a decrease in density of something like 40%. Now, this was just a model prediction, and because it's somewhat counterintuitive, we think of the greenhouse effect as being a warming effect. It seems intrinsic to the concept of a greenhouse. It was treated as a fascinating but academic exercise. Nevertheless, what occurred was that the evidence for this effect showed up a little bit earlier than expected. We created this video for public explanation. It's actually Steve Deo at the Comet program put this together for us, did a really nice job. It's supposed to show the complexity of radiative transfer in the atmosphere. Here are carbon dioxide molecules of, as you saw, anthropogenic source coming off the surface of the Earth and diffusing up into the atmosphere. So these CO2 molecules with the carbon is blue and the oxygen is blue and the carbon atom in the middle. And what they do, of course, is they absorb infrared radiation from the Earth. Here comes an infrared photon. And when the CO2 molecule absorbs it, down in the troposphere, it is quickly deactivated by a collision with some other molecule. That molecule increases in energy, and that's heat. That heats the lower atmosphere. However, as you go up higher in the atmosphere, it becomes optically thin, and the process runs in reverse. The carbon dioxide, it collides with other atmospheric constituents, especially atomic oxygen. That takes energy from the atomic oxygen, and the energy is emitted to space. As it's emitted to space, it radiatively cools the thermosphere. The temperature slowly decreases. The atmosphere contracts. And so you can see if you're sitting here at any one particular altitude, the atmosphere is subsiding below you and the density is going down. So that is the theory behind global cooling in the upper atmosphere. The question is it really going on? Well, this is a little cartoon put together by Jan Lastovica for one of the trend workshops, showing what we think is happening. Of course, you have warming in the troposphere from the greenhouse effect, cooling in the stratosphere and mesosphere, essentially nothing happening right at the mesopause for complex reasons. In the ionosphere, we expect diverse effects, but the ionosphere is very complicated because it's so dynamic and it's affected, in addition to solar and other activity effects, it's also influenced by the evolution of the magnetic field itself. But as you get high in altitude, the thermospheric cooling, which, as you remember, was supposed to be slow but fairly significant, has been well documented by satellite drag data. And this, in fact, is the strongest evidence we have for thermospheric cooling. This was first detected in the year 2000 by Jerry Keating and collaborators. What he did is he looked from one solar minimum to the next and noticed that there was a 5% per decade decrease in thermospheric density. And this finding was later corroborated by three other groups, a total of 4 different groups working in 4 different laboratories with 4 different agendas. These data come from John Emmert et al., who uses literally thousands of objects to estimate the global mean density, and again at our benchmark altitude of 400 kilometers. And then Frank Marcos, who has developed a solar cycle average for this, and then most recently Saunders et al. In the UK have replicated this result with similar findings. The challenge here, of course, is that the solar signal, here represented by this F10.7 index, which is just a solar EUV index, that is to say, it correlates with the solar EUV. Huge changes, order of magnitude changes over the solar cycle. How can you squeeze out this slow secular trend? Well, it's larger than we expected. And that's a challenge for modeling. And showed up sooner than certainly than I believed. I thought maybe in my lifetime somebody would detect thermospheric cooling, and it turns out that just 11 years after it was predicted, Jerry Keating has noticed it, using this fairly simple device of going from one solar minimum to the next. Emmert et al. Do a much more complicated thing where they try to deconvolve this solar signal using indices in order to get an estimate of the global change at all levels of solar activity. So we've moved on from the simple global mean modeling that originally predicted this change and are now running the time GCM. This is the mesospheric extension of the model I mentioned a minute ago. And in order to make global estimates of the change in temperature and the change in density at solar minimum and solar maximum. So the first thing you notice is that the change in density is relatively larger at solar minimum than at solar maximum, because the change in temperature is is absolutely larger at solar minimum than solar maximum. And that is that's because essentially at solar maximum there are other competing sources of cooling, nitric oxide in particular, that change the energy balance a little bit. And consequently at solar minimum, where carbon dioxide is the main cooling agent, it has the most effect. And you can see this in the observational evidence that this is from a plot that John Emmert put together. The blue are his data, his estimate of how fast the thermosphere is cooling in this percent per decade at 400 kilometer metric. About 5% or more at solar minimum. This is, again, your rough guide to the solar cycle, F10.7. 5% down to maybe 2% at solar moderate and solar maximum conditions. And so, again, challenge for the modeling to try to see if the model can agree with this empirical reality, which has significant error bars on it, as you can see. So this is our older result from the global mean model published by Li and Chan et al. In 2006. We do see a solar cycle change in the cooling rate, but we are off in the estimate of at solar minimum. We are underestimating the rate of change at solar minimum, which is perhaps why it showed up a lot quicker than we really expected. However, this more recent work, and it says this work because this is a plot that we showed at the Trend 2014 workshop a couple months ago in Cambridge, UK. So using the fully 3D model, we get a result that's much closer to the data. We have about the right shape to the curve, sort of within the error bars of the estimates with regard to solar cycle variability, and most important, for this key solar minimum metric, we are also getting about 5% per decade change in density at 400 kilometers. So that is a lot of progress, and I think we have a fair amount of coalescence in this field between observation and model. The question is, does anybody really care? I think that understanding global change throughout the atmosphere is an important argument for communicating the reality that we really have a full grasp on the radiative transfer. And of course that includes the stratosphere and mesosphere especially. But I don't think that argument is going to convince climate deniers / skeptics or anybody that doesn't believe that these climate models have any reality. Yes?
I was going to ask if there are any other plausible mechanisms for cooling the upper.
Oh, yes. One in particular being the sun, of course, because so much solar variability is going on. And that is, of course, the greatest uncertainty in this. Nevertheless, I mean, these very careful analyses have tried to deconvolve that aspect of the problem. But there, as far as chemical mechanisms and so forth, actually we have a whole series of papers on the question of, does methane have a big effect? Does ozone have a big effect? Other things. And basically the answer is some of these things have a small effect. They're very important in the middle atmosphere. But when you get up to 100 kilometers, everything gets dissociated, and except for CO2. So it's really carbon dioxide that's having the impact on the thermosphere. That's almost the only source besides the sun and geomagnetic activity, which is also solar in origin. So this argument might have some traction. This is a shorthand for warm down, cool up. It's a shorthand meaning, well, the lower atmosphere, the troposphere, is warming. The upper atmosphere, especially the thermosphere, is cooling. So if you, for some reason, believed that there was no anthropogenic global warming, but instead it was all because of the sun is heating up or something, then you would expect the upper atmosphere to warm even more, because the sun is more variable at the wavelengths that affect the upper atmosphere. But it's not. It's cooling. So this, in fact, is an argument that tends to defeat that particular line of reasoning that leads to certain aspects of the so-called denier-skeptic problem. Nevertheless, I don't know if anybody who has a contrary opinion about this would be convinced by this argument, simply because it is not necessary that it's first necessary that one pays attention to those arguments in order to be convinced by them. Nevertheless, it's a reality, and I think it means that it's worthwhile to try to understand the entire range of the atmosphere and its variability and its secular change in detail. Third reason might be the satellite tracking problem that I was just speaking of, and that's especially important because of the problem of orbital debris, also known as space junk, which is a new issue, not a new issue, but a newly crucial issue in space navigation. And to illustrate that, I'm going to show this video that I got from the NASA Orbital Debris Program Office. It's on the web. You can find it. Just search on it. And it shows every trackable object in orbit around the Earth, larger than a softball. It had this ring out here. This is the geostationary ring, all those communication satellites. There's also a geosynchronous population. You see that there? Then you can see all these objects in middle Earth orbit, GPS satellites, and elliptical orbits. Then as you come in closer, you see this incredible cloud, over 10,000 objects in low Earth orbit, each of which must be tracked, each of which must be avoided anytime you want to launch something or navigate something like the space station. And as that population increases, that problem becomes worse and worse and makes itself worse through interactions with itself. That is to say, the cloud. There's that geostationary ring again. So this is now a popular subject. I've been using this movie as a prop for almost a year now. And I finally saw the movie on the plane on the way back from the Trend 2014 workshop in England. And let me tell you, it's a real bomb. It apart from the unphysical aspects and the violations of the laws of motion, the thing that I couldn't stand about was the soundtrack. Every time there's something happening in space, there's a soundtrack. You know, who knew that space had a soundtrack? I was looking forward to these vast, silent explosions because the special effects are good. And anyway, don't bother with the movie, but you might read the New York Times, which points out that the movie, although criticized for scientific inaccuracies, is not a fantasy because space junk is very important. And they go on to point out that adherence to the international conventions regulating objects in space will go a long way to mitigate the problem of space junk. And nevertheless, compliance is always a problem. Now, at the meeting, at the Trend 2014 meeting, you know, we've been saying, in order to justify the research we do for some time, that we need to understand these things, that we need to track satellites, that we need to get a handle on the space junk problem. We've been saying that rashly, but it turns out it's all true. Hugh Lewis gave a great talk in Cambridge of actual numerical calculations that they're doing at Southampton with all of these objects and their likelihood of collisions and the repopulation by new junk or new satellites. And so this is a probability distribution resulting from many, many runs of their model. And it assumes 90% compliance with those international regulations that having to do with making sure you deorbit the shrouds and the couplers, and not blowing things up in space turns out to be very important. And so, assuming 90% compliance, the population increases, stabilizes. It's still very large, 18,000 trackable objects. This doesn't even include things smaller than a softball. But with an anthropogenic trend in his model, you get a continuing increase and spread of this crowd. That means that the uncertainty is increasing, because as the atmosphere gets thinner, junk has a longer lifetime. The population increases. The likelihood of one piece of junk hitting another piece of junk, or as happened recently, a piece of junk hitting something that was actually a valuable satellite, the so-called iridium collision, as that becomes more possible, the spread of possibilities gets worse. And in fact, you know, some of these runs are very deleterious. 40,000 objects in space would virtually make it very difficult to navigate in low Earth orbit. So that's one reason why an anthropogenic trend in the density of the upper atmosphere might be important to understand, might be important to track, and might be a motivation for adhering to those international conventions. So you asked if there's anything else going on. Well, here's that long-term satellite drag data plot from John Emmert again, showing the 5% per decade decrease at solar minimum. But then, in 2008 and 2009, something else happened. The thermosphere abruptly dropped by 30%. We thought we were at solar minimum in 2007, and then the thermosphere got 30% lower, well outside of the range of expectation from any sort of atmospheric effect or anthropogenic effect. And that's true even though this F10.7 index hardly went lower, it went a tiny bit lower. But even so, there was a lot of evidence that something else was going on the sun. Here's that sunspot plot again, looking at 250 years of data. You can see that there's very long solar minimum here and low activity, and then followed by what appears to be a very weak cycle. It's a lot of evidence that magnetically speaking, things are going down. This is a plot that Juliana de Toma showed just last week of the magnetic field of the sun represented by its interplanetary strength at the L1 point. And there may very well be a trend here over somewhat longer time scales. What's unquestionable is that these are historically low values, and here's that weak solar cycle we're coming into now. Here's a plot that Scott McIntosh put together, showing a variety of parameters, ranging from helium content in the solar wind and purple. Here's a really interesting one. The turquoise or cyan dots are the cosmic ray flux, but inverted, because the cosmic ray flux is higher at low solar activity, lower at high solar activity. So to aid the eye, he just inverted the curve. And you can see that as we go into this solar minimum, we're in a period where the cosmic ray flux is at historic maxima for as long as it's been observable. And then, of course, there's the total solar irradiance. This is potentially very important. Those are the red dots from the Virgo instrument on the SOHO spacecraft. And here's the solar cycle. We don't have that long a record from just Virgo, but it appears that total solar radiance during this solar minimum period was a little lower, maybe 100 parts per million, than in previous solar minima. But that's controversial. The TSI guys are going to be arguing about that for probably at least another solar cycle. Am I right? Here's another one from Juliana showing the structure of the corona changing from its very dipolar look that it typically has in solar minimum. See if this is from 96 to can you see this okay? To this sort of chaotic, weak, structured. It's not a solar maximum look, but it just seems off for solar minimum. And this is not unique, as she pointed out. It's been seen before. This is the 2009 corona during an eclipse, showing it's sort of dipolar, but it's got this sort of chaotic structure to it. And this is from the archive of the eclipse archive that Phil Judge put together, going back over 100 years to the last time we had a solar minimum this week. And I intuit that there's other people in the audience who were involved in putting this archive together. Maybe Don helped with this, and you have a similar technology isn't as good, but you have a similar structure, look and feel at any rate to the corona. So maybe this solar minimum behavior is different from our recent experience, but perhaps not unique in the history of the sun. So we looked at solar EUV indices. I know you can't read this, so I'm going to show the change in various things that represent the EUV flux. This is an actual measurement of the EUV flux, but the calibration is controversial. What I've done here is shown the minimum to minimum change as a fraction of the minimum to maximum change. So I've sort of normalized out the solar cycle, expected solar cycle variability. Based on these measurements, this is the sunspot number, Lyman alpha and magnesium 2, we think that the solar EUV flux was down about 10% compared to the previous solar minimum. We use that as input to the TIE GCM. We find reduction in temperature. We find reduction in density. These include lower solar EUV. They also include the lower levels of geomagnetic activity, and it also includes that anthropogenic increase, which is a small part of this, 5%, but non-negligible. And so I will now show you something that I didn't show when I showed this very impressive looking plot before, which is that at this solar cycle, at this 2008-2009 solar cycle minimum, the densities in the model and the measurement were 30% lower. So we're getting, with those assumptions, we're getting good agreement between the model and the measurement. Consequently, we think that we have a handle on what the sun did to change the atmosphere. And well, I'm going to skip over the ionosphere, but basically we expect the ionosphere to also change, in this case by about 15% from one minimum to the next. And the model global mean kind of agrees with this this ionoson-based index, which also shows a 15% decline in actual ionospheric measurements from one solar minimum to the next. Oh, there it is. So, when Hugh Lewis runs his debris model, here's the baseline run, and puts in the anthropogenic trend and the possibility that solar activity might be quiet for a while, we now get a cloud of probability distribution that goes from bad to runaway. And that is somewhat alarming. Now, here's what all he did was he imagined a Maunder minimum-like period for about 50 years that ends here, but even after it ends, we don't recover. And it could be a lot worse than this, because his assumption of what solar minimum looks like is it just looks like sort of perpetual solar minimum. And we now think that maybe, at least in the EUV, and at least in the thermosphere, that a Maunder minimum-like period might be a lot quieter, a lot lower, a lot cooler than a typical solar minimum. I'm going to move on to the next. Well, here are the conclusions, just briefly stated. The reason solar minimum was lower than usual, I use the words typical and usual in quotation marks. EUV, geomagnetic activity, and CO2, we're still sorting out the relative importance of those things. But the reason I have these things in quotation marks is because in the future we're not going to be able to calibrate anthropogenic change just by going from one solar minimum to the next. There is no such thing as a typical solar minimum. So here are the questions. Maybe they motivate research. Solar cycle 24. I think it's unquestionable now that this recent solar minimum was the deepest in a century, certainly the longest. Solar cycle 24 appears to be the weakest in a century. And what happens next? Of course, nobody knows, but a comprehensive understanding of the solar dynamo will help. And here are 3 recent papers describing this work. Before I go on to the next segment, are there any questions about, or save your questions for the end if you need time to think about them. But I'm going to move on and sort of change the subject here. So I'll pause for 1 minute. Just a few minutes, I'm going to try to discuss what I consider to be some of the frontiers in solar terrestrial physics and challenges for the High Altitude Observatory within that context. And just as a starting point, we might as well look to the recently released document, Solar and Space Physics, Science for a Technological Society. This is the so-called decadal survey that has participation from many space scientists, solar, upper atmosphere, magnetosphere, heliophysics, nationwide. And the recommendations are summarized with these 4 main points. Especially, determine the origins of the sun's activity and predict the variations. Determine the dynamics and coupling of the Earth's magnetosphere, ionosphere, and the atmosphere. And determine the interaction of the sun with the soul. Well, this is pretty broad. But the document does have, under each of those points, a more detailed list of exactly what is needed to be done. Not going to go through the whole list, but I will point out that there's one additional recommendation that I think is very important to us here, which is that to make meaningful scientific progress, the Sun, heliosphere, Earth system must be studied as a coupled system. This is the so-called system, science, and imperative. And I certainly agree with that, and I think that HAO has a contribution to be made there. Of these national goals, it's not possible for a medium-sized organization, even a broad one such as HAO, to be able to address every one of them. We have to pick a few. And of those, I think the ones that we're best positioned to address are the space weather questions, the space climate question, and then this interconnections between the lower and upper atmosphere. And these lead to specific things that we can do. We can develop and lead observational and theoretical programs in coronal magnetism. We can collaborate with heliospheric modelers on those things to bring the effects to Earth. We can study the solar dynamo and perhaps develop a community model of the solar dynamo. We should be working very hard to extend WACCM, the whole atmosphere community climate model, into the ionosphere. And we want to exploit these high-resolution capabilities of NCAR dynamical models to examine these instability questions, especially in the equatorial ionosphere, and partner with some of ionospheric physicists we are already working in this area. Now these are all in the HAO strategic plans, but they're frontiers. And in the recent past, frontier has meant wish list, things we want to do, but wish we had the resources to do. So what I'm saying is that our frontiers need to become our imperatives. Here's the lead one of these decadal survey recommendations. Understand how this sun generates the solar cycle. Why does it? What causes it? How does it vary in intensity? I think we're poised to answer these questions from what I see of the dynamo modeling that's occurring in the High Altitude Observatory, and I think we need to coalesce around those goals. Especially because I want to know about solar irradiance, ultraviolet irradiance, and ultimately total solar irradiance, and how it responds to solar cycle variation and how it might respond to extended changes in solar cycle variation. Because it might even be important not just for the upper atmosphere, but for the atmosphere. And even if it isn't, it's our obligation to find out. We want to understand this explosive release of magnetic energy. This is a CME simulation that Yu Hong Fan did. Now, we don't really do heliospheric modeling here, carrying these CMEs all the way to the Earth, but we can partner with people that do. And I think that is a key area where we need to broaden our participation. Let me illustrate this by showing this event that occurred last week. There's a coronal mass ejection on September 10th. Very spectacular. A lot of people were asking me, are we going to see the aurora? And of course my answer was, well, it depends if the sky's clear or not. And now the Space Weather Prediction Center takes data of this type. They now actually use real numerical models. This is Dushan Odrasil's Enlil model of the solar wind. They feed a pulse essentially into it, and then they predict how fast it will propagate out through the heliosphere, the density and the velocity. And they predicted that at late in the day or midday on September 12th, this shock would reach Earth and increase the solar wind speed, geomagnetic disturbance. So they predicted there was also an earlier CME that caused this little bump. So they predicted a moderate geomagnetic storm on September 12th and a major geomagnetic storm on September 13th. This is a great thing, space weather prediction. Let's see how they did. Well, this is just the KP index, coarse index of magnetic activity. September 12th, this is that first event coming, very small storm. Then September 13th, arriving in the afternoon, right on schedule, here comes the storm. KP6 went up to KP7. That's pretty good storm, maybe even visible in Boulder. And then it just petered out. And the storm that they predicted for September 13th never happened. And the skies cleared right as the sun went down in Boulder, and people went out. I'm looking at one of them who went out and spent all night looking for the aurora. Little did you know that what happened was, I know these plots are messy for those who aren't used to looking at them, but just look at the yellow here. This is the wind speed. Solar wind, boom, here's the predicted event, and sure enough, the solar wind shot up and we had some activity for a little while. But look at the interplanetary magnetic field, the strength in white and the north-south component in red. North-south component is very important for magnetospheric coupling. When the north-south component goes south, strong coupling and a storm. And here it is. Late in the day on the 12th, we got a little storm. And then what happened is the interplanetary magnetic field vector rotated way back into the north. And even though the field was very strong, it just sat there and petered out, and we got practically nothing. So the moral of this story is, if you want to predict space weather, it's not enough to predict the solar wind. You have to predict the interplanetary magnetic field. How are you going to do that? Well, maybe these measurements of coronal processes and the underlying magnetism in the corona and below it have some information that can be used to drive a solar wind model in a more realistic way. And this is a very sophisticated model. It has a magnetic field, but it's a slave to an inner boundary condition. So this is one place where we can make a huge contribution by informing these sophisticated models of space weather as to what is going on in the sun. What will we do if we had this information? Well, now we would have something that we could feed into these sophisticated magnetosphere, ionosphere coupled models that show what happens when an auroral storm impacts the... I'll just kill the lights for 1 second so you can see this magnificent video that Tim Guile produced of the auroral storm impacting the magnetopause, the distortion of the field lines, and the increases in auroral luminosity, ionization, heating, and other high-latitude processes. I'm going to stop it there and move on. It's a fairly long video. Here's another thing that's really important to the nation and to physics. There are these instability processes that occur at the low latitudes. You can see these dark spots, which are bubbles or irregularities in the ionosphere. These are very disruptive of communication, navigation. They destroy the ability to use GPS, and they occur over regions of the world that are important to the national interest. So understanding how they work, well, there's been a lot of progress in understanding how they form in the presence of these electric fields that elevate the nighttime ionosphere. This is an animation by affiliate scientist Joe Huba. But the mystery is, why do they happen on some nights and not on others? There's two schools of thought. One is that it's all about the ionosphere and its configuration. The other is that atmospheric processes, neutral atmosphere processes at the turbopause, determine whether or not there's enough seeding to generate these instabilities. We have the capability of examining these questions using high-resolution modeling that is facilitated by some of the main advances in dynamics and computational power that have occurred here at NCAR. So, in terms of an overall scientific vision and agenda for HAO, well, we put something together last winter. Steve Tomczyk motivated a series of meetings. I did a lot of scribing on it. And this document, it's you can find it on the download site if you want to read the thing. I just sort of summarized it here. It's a one-pager. The idea was, can we summarize some kind of consensus in one page of where we think we should be going? Now, consensus is never perfect. It's never possible to get everybody to agree to everything, and certainly nobody agrees to everything in that document. But at least it's a starting point for uniting and motivating our efforts. I put this in here, and I expected people to shoot me, but it's still there. I think that the High Altitude Observatory needs to focus on the solar problems that most impact the Earth, especially its upper atmosphere, its ionosphere, its magnetosphere, because that is where we have the most societal consequences, and that is what links us to the National Center for Atmospheric Research. So that's my platform. And it's now everybody's platform because we all wrote it down and said, this is our document. Challenges we face are extensive. How on earth are we going to solve these difficult problems during times of decline? I made this plot in Excel because it sends a powerful message. I know how to make a plot in Excel. But it shows a really precipitous decline. And of course, this occurs across all staff. And you might think that project scientists take up some of the slack, but they don't. We have really suffered losses in the scientific agenda of the observatory, and that needs to be reversed. So where do we go? First of all, we need to reverse that trend. We need to hire. We need new blood. I say bread and circuses. I'm just joking around, but when I say bread, I mean dough. I mean dineros, moolah, euros, yen, Swiss francs, kroner, anything we can find. And that business and the advocacy of the observatory is the responsibility of everybody, not just the director. That's my talk. I have this little coda because Tom Bogdan has been talking about the importance of this management book that says that an organization needs to focus on the main thing that it does, and the idea behind it is that the fox knows many things, but the hedgehog knows one big thing. What that means is that, the hedgehog knows one big thing. It can protect itself by rolling itself into a little ball and playing dead. I just don't know if that's the right image to carry us into the future. Because it works great for foxes if the fox is trying to kill you, but if there's a truck coming down the road, it's really not much of a strategy at all. Anyway, we found the hedgehog in Cambridge at the Trend 2014 workshop. Here he is. He's very cute, but I don't think it's a motivating concept. So that's my summary. Thank you for coming.
At this point, I turn it to you. So if there are any questions, raise a hand. Whoever raises their hand first.
I'm going to raise my hand, so I might as well do it. So Stan, I'm wondering, I agree with you, we need money. But I'm wondering where you think the balance is between enough grant money and needing more grant money, and what your role would be in terms of either coordinating staff around large initiatives or kind of to each his own approach that we have right now, and how you see that as a fit within HAO.
Well, the best strategy is to have the full range of a Kolmogorov spectrum. I know you don't know this stuff. You want a full range of sizes, and we're blessed because we have this big chunk of base. Maybe it's not as big as it used to be, but it's still there. And then you want big projects, medium-sized projects, little projects, and tiny projects, because they each have their own characteristic frequencies. So all of those things are good, and there is no perfect balance. What we mostly need in that regard is more teamwork. Many of us, and that's why I said advocacy is a responsibility of all staff, many of us are very good at advocating for our own program, for our own grant, or for our own scientific visibility. It has to become instinctive within the organization that when somebody says, "Oh, that was a great talk," or "You did such a great job with that model," that the response must be, "Well, HAO did a great job. The instrumentation group built a great instrument. The software development team built a fantastic model." And And that will help unite us behind some of the larger projects that is absolutely imperative to bring in, especially for instrumentation support. You can't maintain an instrumentation group with a series of tiny little things. You need some main projects to work on. So, but there's no perfect balance. Income is always a good thing, in my view.
Other questions? Both parts of the talk are open to questions, so feel free.
How are you going to turn the frontiers into imperatives? New money or reallocation? Especially because that was the one that called out whack-a-mech, so that's why I'm interested.
Can we have a question from an HAO person, please? Now, Dan is honorary HAO, being a postdoc at HAO, and I think for one thing, well, let's address the one that's foremost in your mind. How are we going to increase HAO support for development of the whole atmosphere community climate model? Well, we have to continue to get grant support, as we have been in the past, to do that. We have to continue to leverage the collaborations with the other divisions. And we have to, since Jim Hurl is in the room, we have to go to the NCAR directorate and advocate for the idea that this flagship NCAR product needs more support for its extension into the ionosphere, which is its destiny. Now, at the same time, our section has to change its focus. The AIM section, whose bread and butter depends to a great degree on our heritage models, have to find a way to move on, cut the cord on some of them. We've already I showed some global mean results, but we're implicitly pulling the plug on the global mean. We can't just, it's too old. We have to move on. And we have to adjust our research focus on our grant proposals to exploit the new reality. So yes, reallocation and when necessary. In certain regards, that could be a very difficult process, but it doesn't mean that anybody's going to stop doing important and exciting things in their field. It just means that they need to refocus them on things that are more compelling for the observatory, center, and national agenda.
Other questions? Question in that. Maybe the microphone can be passed.
Now, you started out your presentation with reference to this decadal study. And in that decadal study, there is sort of an assumption that I find...
Keep in mind that one of the lead authors is present.
Is quite pretentious. And at least with reference to the sun-climate connection, and that is... we don't know to what degree prediction is even possible in the physics problem that we are dealing with.
For the solar part of it especially.
Yes.
Yes.
And for that reason, there remains a necessity for basic research, not for some fine-tuning in terms of an analog to numerical weather prediction.
Absolutely.
Do you agree with
I absolutely agree, particularly with the solar dynamo, solar cycle problem. This is a frontier area where basic research is needed just to get a full physical picture of how the dynamo works. If we could do that, and that's, I think, in progress. I feel like it's almost a reality, and it will be an enormous step toward understanding the solar cycle. Predicting the solar cycle, for many reasons, we all know why it's a hazardous game to try to predict the solar cycle, but maybe we can try to understand the limits of its variability. And one thing that I find intriguing and is, I think, a great example of solar physics being responsive to other priorities is the endeavor to be able to say something meaningful about the range of total solar irradiance that might occur over the range of solar variability, and also, of course, with respect to the spectral irradiance and the ultraviolet variability. So that's that's one of the challenges HAO faces. You have a whole spectrum of things leading from the almost operational to the completely unknown. And different flavors of research are called for in all of those areas. But in order to motivate research into the solar interior, the solar dynamo, and the solar cycle, we need to cast it in a way that causes it to mean something to people that might care about it.
Stan, how do you identify who those idea makers are within HAO? I mean, to get all on the same page, to get, to understand where we're going forward and everybody buy into that. How do you?
I think we made a lot of progress in that regard last winter, just by having a rolling cast of characters that virtually every scientist and many other people, almost everybody at HAO contributed to this process of having an open discussion and rethinking of where we're heading. The only scientist that refused to come to a meeting, I cornered him at lunch and said, "Well, tell me what you really think, because I need to know." So he even contributed. No, it's not. He contributed even though he didn't want to, because he had a jaundiced view of strategic planning. And so, a strategic vision has to be a shared vision in a scientific organization. And it's the job of the leadership of the organization to make that happen. The other answer to your question is where the new big ideas are going to come from? Simple answer. New people. We don't have any scientist ones in the organization. We don't have any scientist twos in the organization. We don't even have any project scientist ones, except for one. And we don't think our prospects for retention are high. And it's a short-term situation. And so we need some junior scientists. That's where all the new ideas come from. Everybody knows that.
We have time for one quick question. If there is one more quick question.
Sort of going more to the scientific content of the talk, when they were making those predictions of the amount of debris, did they try and put a dollar cost onto it?
Yes, but I would have to pull up Hugh's presentation to delve into that. What they want to do really is go capture the largest and most dangerous objects, and that could be a very expensive proposition, although a very effective one. And therefore, because it's expensive, you have to calculate the cost savings. And so that group is doing work in that regard. But as you can see, the main message there is the uncertainty. As the atmosphere declines, the uncertainty in the spread of junk, it becomes larger and larger and larger. And that doesn't even count the stuff you can't track.
You are just getting warm up with questions, but I will have to stop that. I have to stop this now. Our schedule calls that we make a transition. We being me, Stan, Stan, me, and the HAO staff back to the Center Green. And the next, so at this point, I would like to thank Stan. Let us thank Stan for both presentation and his answers. And then invite everyone HAO staff who would like to attend the next session to walk over back to your campus, and Stan and I will meet you there. Thank you all for attending. I hope to see you tomorrow at the same time, same place.